Check it.
Okay, welcome back. Today we're going to be talking about the fundamental theorem of algebra and imaginary roots. So we have been graphing functions in factored form up until now. And if you can see the factors, then you can see the root that's created by each factor. But what if you go to factor something and it's not factorable, or only part of it is factorable? So watch what happens with example A here. We're going to start off here. We're asked to find the roots and sketch the graph of x to the fourth minus 81. Now this is a fourth power function. A fourth power function is going to have up to 4 roots, 4 x-intercepts. But how do you factor this, right? You might look at it and go, well, I don't know how to factor this. Well, here's the thing. This is a difference of squares. Whether or not you realize it, it's a difference of squares. This is something squared, and this is something squared, and there's a minus in between, so it's a difference. It's a difference of squares. And we do know how to factor a difference of squares. We just have to understand what's being squared right here. What do you square to get x to the fourth? Well, you square x squared, don't you? You take that and you square it. And what do you square to get 9? Sorry, 81, Freudian slip. You square 9, right? And that's what you square there. And then there's the minus in between. So this is a difference of squares. So if you want to write it as a difference of squares factored, it's going to be something times something. It's going to be x squared minus 9 times x squared plus 9. Because when you have a difference of squares, it's a plus b times a minus b, conjugates. So you look at this now and you go, hey, well, hold on a second. Now this is also a difference of squares, right? This kind of looks like a y there. Let me make that an x. So this right here, this is also a difference of squares. This is something squared minus something squared. This is x being squared and 3 being squared. So this part right here can be factored as well. And this gives you x plus 3, x minus 3. Now is this a difference of squares? Can you factor that now? Well, this has a plus in between. It's a sum of squares. And there's no factorization for a sum of squares. You can't factor it. It doesn't work. So this does not factor. So what does this mean? It means that we can set all this equal to 0. Okay, with the zero product rule, when you want to find the x-intercepts, you make the y 0, right? That becomes a 0. And now you have a factor times a factor times a factor equals 0. And you go to use a zero product rule, and you can get 2 real roots. You can get x equals negative 3 for this one. You can get x equals 3, positive 3 for this one. But what do you get when you try to do this? Well, this is not factored, first of all. And secondly, it's not solvable without getting an imaginary answer. Watch what I mean. Let's try to solve this. Let's go over here in the scrap area. X squared plus 9 equals 0. And what do? The first thing you do is subtract 9 from both sides, right? And you get x squared equals negative 9. Well, right away, there's a problem. There's no way you can square a number and get a negative. It's not possible. It's not possible. So right away, you're in la-la land here. You're in imaginary territory. So since we know this is going to be imaginary, let's go ahead and finish this up. Let's square root both sides. Okay, and you can see there's a square root of a negative number there, which is not going to be real. What's the square root of x squared? It's the absolute value of x. What's the square root of negative 9? It's 3i. If you remember, it's the square root of 9, and then this is an I right here. It's going to create an I, so 3i. And when you drop the absolute value bars, this becomes plus or minus 3i. And if you really want to be thorough and put in a plus bi form, it's 0 plus or minus 3i. So what we end up having here are 2 imaginary roots. Okay, x equals 0 plus 3i, and x equals 0 minus 3i. Those are 2 zeros, roots, x-intercepts, right? But they're imaginary. So we have 2 real roots here, 2 real zeros slash roots slash x-intercepts, whatever you want to call them. Okay, x-intercepts. And here we have 2 imaginary or complex roots or complex zeros or complex x-intercepts. So complex imaginary, because they're imaginary, you can't graph them. You can't see them. They're imaginary. That's the whole point of being imaginary. You cannot see them on the graph. However, they are there, all right, in the sense that this is a fourth power function, and this should have 4 roots, right? It should have 4 roots or 4 zeros or 4 x-intercepts. But it only has 2 when you go to graph it. Why? Because only 2 of them are real. There are going to be 2 that you don't see, and that's the ones that we have here, the imaginary ones. So when you do the graph, you only worry about graphing the real roots. So what are the real roots? -3 and +3. So -3 and +3. There's your 3. There's your -3. Okay. And what is your end behavior? Well, this is a fourth power function, a positive fourth power function. There's no negative in front of the x to the fourth. So it's an up, right? Even powered function, up, rocky, right? So what it's going to look like basically is something like that, where it's going up on both sides. Okay. And you might say, well, what about, okay, so it's a fourth degree function, but it only has 2 roots. Why aren't there 4 roots? Because 2 of them are imaginary. Do the imaginaries show up here? Not really, no. They might cause some curves, in the function later, but not necessarily. So I'm not going to really worry about that. Okay, the important thing is there's only 2 real roots, and the 2 real roots end up on the graph. So if I ask you the question, how many roots does this have? The answer is 4 roots, 2 real and 2 imaginary. And if you want to see what the imaginary roots are, take the unfactorable, factor. Like this factor right here cannot be completely factored because, you can't factor x squared minus x squared plus 9. And you can solve it for, set it equal to 0 and solve it, and you will see the imaginary factors right there, the imaginary roots rather right there. Okay, so the idea today is something called the fundamental theorem of algebra, which basically says that if you have a function of a certain degree, like in this case it was degree 4. If you have a 4th degree function, you should have 4 total roots. However, not all of them are necessarily real, right? Some of them might be imaginary. Now, just to be clear, when we did the imaginary roots here, okay, you notice that what happens with the imaginary stuff is that you get a plus or minus. So they come in pairs. You cannot get a single imaginary root. Imaginary roots or complex roots, they can only come in pairs because it's always a plus bi, a minus bi. It's always like this. So if you get one imaginary root, the other one has to be the conjugate. There's always going to be in pairs of 2. So is it possible with a 4th power function to get 1 real and 3 complex or 3 imaginary? No, this is not possible because the complex roots, the imaginary roots, have to come in pairs. Pairs only. Okay? So what are the possibilities here? The possibilities with a 4th power function are you get 4 real roots, 2 real, 2 imaginary, or 4 imaginary. All right? But you cannot, that's it. Those are the only 3 possibilities. You cannot get like 1 real and 3 imaginary, and you cannot get 3 real and 1 imaginary. That doesn't happen. So as long as you understand that the imaginaries come in pairs, you get the idea. All right? Let's try another one. So now this one is sort of factored. I mean, it's not fully factored, but it's sort of factored. So let's see what we can do with it. This one right here is a difference of squares, right? It's something squared minus something squared. What do you square to get x to the 4th? X squared. What do you get? What do you square to get 16? 4. So one's going to be a plus and one's going to be a minus. How about this here? That's a difference of squares. What do you square to get x squared? You square x, and what do you get square to get 25? 5. So x5, one's a plus, one's a minus. And here, x plus 3 is already factored. Now look at this again. Is this in fully factored form? No, because here's another difference of squares right here. Difference of squares. So we have to keep factoring. It has to be fully factored. Can you factor this? Is this a difference of squares? No. That's a sum of squares, which is not factorable. So that's going to produce some imaginary roots right there. We'll just write this down for the time being, x squared plus 4. We can't factor that one. But this one, what does this become? This becomes x plus 2, x minus 2. And all the rest of these we'll just copy. So let's go ahead and graph this thing. Well, before we graph it, let's take a look at this. This is not factorable. So if you want to see what the imaginary roots would be, you can come over here to the scrap area, x squared plus 4, set it equal to 0. You'll have to subtract 4 from both sides. You'll get x squared equals negative 4. You'll square root both sides. You get the absolute value of x equals, what's the square root of negative 4? 2i. You drop the absolute value bars, and you get 0 plus or minus 2i. Those are two imaginary roots. Okay, two imaginary or two complex roots. Roots slash zeros, whatever you want to call them. So we know two of the roots are imaginary. How many of them are real? Well, we have 1, 2, 3, 4, 5 real. So we have 5 real zeros, roots. I'm going to call them roots from now on. 5 real roots and 2 complex roots. Complex and imaginary. The right word is complex, but I keep saying imaginary because they're sort of synonyms. 2 complex roots. Now, that's a total of 7. What's the degree of this function? Well, you can see this is x to the 4th. This is x squared, so that's a power of 6 so far. And 1 more gives you a power of 7. So this is a 7th degree function. Okay? And it has 5 real roots and 2 complex roots. That's the fundamental theorem of algebra. The fundamental theorem says your total roots must add up to the degree of the function. So we have 5 real roots, which we can see right here. We can see them. And we have 2 roots that come out of this unfactorable part. So we have a total of 7 roots. Now let's go ahead and do the graph. This is a 7th degree with no negative in front of it. So it's a cubic, i.e. a travolta, up on the right, down on the left. That's the end behavior. We have roots at 4 and we have roots at 2 and negative 2. So we'll put a root there. We'll put a root there. We have roots of 5 and negative 5. We'll put a root here. We'll put another root here. And we have one at negative 3, which is right here. Okay? And we're starting low down here, and we're ending high up here. So we have to start low. Now, none of these have a multiplicity to worry about. So we're just going to go through all of these. And we just have to make sure that we start low and end high, right? We end up here, and we start down here. So I'm going to do my best to make a nice smooth curve. Let's see if I can do it. To the edges of the graph. I'm going to start down here. Well, it's easy for me to go this way, like that. And like that. Go down this way. Curve back up. Curve back down. Curve back up. And you know it's a good sign when your end behavior ends up correct, which is I ended up here. If I finished this whole thing and I was pointing downwards, then I made a mistake somewhere, right? Or I didn't bounce off of something I should have bounced off of. All right, and there you go. So that's that. And sketch the graph we just did. Now, how many real roots are there? 1, 2, 3, 4, 5. Those are the real zeros. But how many zeros are there in total? Well, it's a 7th degree function. There's supposed to be 7. That means 2 of them are complex or imaginary. Okay. All right, let's do one more and call it a day. We have this function here, which is, there's an x squared here, right? You know what? Let me change this a little bit. Let me make this squared. All right. And you'll see why in a moment. So what's the degree of this function? Well, you have an x squared here, which is a degree of 2 so far, right? And this is x squared, so that's a degree of 2, but then that's also squared, so that's another degree of 4 right there. And this one's a degree of 4 right here. So what's the degree here? This is a degree of 10. This is now a 10th degree function. And it's got a negative on it. See the negative? So its end behavior is down, rocky. Okay, upside down rocky. So we know it's a 10th degree function. How many roots should it have? It should have 10 roots. Okay? The question is, how many of those 10 are real and how many of those 10 are complex / imaginary? So we're going to have to fully factor this thing. Let's see if we can fully factor it. So we have f of x equals negative. This is x plus 2 twice, right? X plus 2 times x plus 2. There's 2 imaginary roots right there. Now, I don't have to write it twice, but I'm just writing it out. You know, you can leave it like this, but I just wanted to write it twice so you can see there are 2 roots there. This one twice, a double. And now here, can you factor this? And the answer is no, you can't. So this one is not factorable. It's a sum of squares, not a difference of squares. Now this one, is this a difference of squares? Yeah, it is. This is x squared squared, and this is 4 squared. So x squared and 4, x squared and 4, one with a plus, one with a minus. Okay? Now you look at that and say, what else can we factor? Well, actually, this right here is a difference of squares. So we have one more factoring line to do. This negative, this x plus 2, x plus 2. Okay? This right here, I'm going to put this, we know this is not factorable, so I'm going to put it on the end here because it's imaginary with the squared. This is also unfactorable. This is a sum of squares, so not factorable. It's imaginary. But this thing right here, this is definitely factorable. This is x, the thing squared, minus 2, the thing squared, right? So x and 2, 1 plus, 1 minus. And now you can see, hold on a second, you have 3 x plus 2's there. See that? So we can now rewrite this in grouped form, fully factored but grouped. This is f of x equals, there's a negative there, and we have 3 of these now. So x plus 2 with a multiplicity of 3. Now that's odd, so we are going to go through it. We're not going to bounce. Then we have a single x minus 2. That's a real root as well. So you have 3 real roots here, or a triple real root here, which is the same as 3 reals. 1 more real, so that's 4 reals. And now the stuff that comes out of here is all going to be imaginary because this is not factorable. Now I could do what I did over here and solve it, but I'm not going to bother because just take my word for it. If you set these equal to 0 and try to solve, you will get imaginary numbers. Well, this one we already did like twice already, but if you do something like this right here, if we just try it really quickly, I'm not going to do the whole thing, but I'll just show you that it's going to lead to an imaginary. If we come over here in the scrap area, x squared plus 16, the whole thing squared. If you set that equal to 0, the first thing you're going to do is square root both sides. That'll knock off the square here, and this square root of 0 is still 0. So then you get x squared plus 16 equals 0, and the rest of this is just like the other one, where you get 4i plus and minus 4i. Okay, and you actually get it twice. You get plus or minus 4i with a multiplicity of 2. So anyway, long story short, you're going to have 3 real roots, 4 real roots, and then this is going to be 4 imaginary roots and 2 more imaginary roots. Okay, so we're going to have a total of how many? Well, let me just copy this down. This is going to be a total of 4 real roots that you're going to see on the graph. This will be a triple, so it'll only look like just there's only 2 because there's going to be 1 triple and 1 single, but still it counts as 3 real roots here. And here, this is going to be 4 imaginary, and this is going to be 2 imaginary because 2 times 2 is 4 imaginary that you can't factor, and 2 more. So this is going to be 6 complex roots or imaginary roots. And does that add up to give you a 10th degree function? Yes, it does. And that's the fundamental theorem of algebra. That's what the fundamental theorem tells you. It tells you that whatever degree your function is has to be the sum of the complex and real roots. All right? So if I ever give you a problem that's, let's say, 9th degree, well, then these 2 numbers better add up to 9. That sort of thing. All right, let's go ahead and graph it now. We only have 2 numbers that we have to put on the graph, positive 2 and negative 2. So here we go. Positive 2, that's the single root, and negative 2, that's the triple root. Okay, so you could think of it as 1 root, 2 root, 3 root. There's actually, so it's 1, 2, 3, 4, right? 1, 2, 3, 4, like that. And that's your 4 real roots right there, even though it looks like only 2 of them. And now, what's your end behavior? Well, we said this is a negative Rocky, right? Upside down even root. So we're going to be going down and down on both sides, right? And so basically you're starting low. You're going to go through these and come back the other way. Now, since this is a triple root, there is a little bit of a wiggle to it. So I'll draw the wiggle, but you don't have to worry about it yourself. So it's going to be not quite straight. Like I said, if you don't know what I'm talking about with the wiggle thing, don't worry about it. I'm not requiring it. But down on this side, up on this side, and then come down, and that's it. All right. So if you drew it as, by the way, what I'm trying to say is if you drew it just like this, where you just came up and came down without this little wiggle part, don't worry about that. That's fine. But this is it, and we're done. So just keep in mind, fundamental theorem of algebra just says the degree of the function has to equal the total number of real roots plus imaginary roots. And don't forget, imaginary roots have to come in pairs. So from the possibilities standpoint, if you have, this is a 10th degree function, for instance, what were the possibilities? Well, the possibilities were that you would have 10 real and no imaginary, 0 complex. Or maybe I should, anyway, or you could have 8 real with 2 complex, 6 real with 4 complex, 4 real with 6 complex, which is what we have up here, right? 4 and 6. 2 real with 8 complex, or no real but 10 complex. The point is, these have to, the ones on this side here, the complex ones, these have to be in pairs. They have to be even numbers. Okay, and that dictates that you cannot have 9 reals or 7 reals, or, you know, it has to be, they go down by 2s. And these are the possibilities. This is the one that we happen to get in this last example, but just keep that in mind, and that will be on the quiz. Okay, guys, see you at the next video.
Check this.